was conducted to investigate by means of finite element analysis the nature of stress distribution in the temporomandibular joint, that is TMJ, compact bone and other components. They're caused due to chin-up forces applied in varying direction. So in this slide, the images what you're seeing is a typical geometry, which is in isometric view, the front view, top view, and other side views for a better understanding of a geometry. So once we receive, once we model the geometry, that is in the form of infinite degrees of freedom. So that infinite model is converted into finite element model by using different meshing technologies. So in this particular, typically there are two types of meshing practices. One is manual meshing and auto meshing. So in this project, we have adopted manual meshing because of the complexity of the geometry and difficult, shape, difficult, it was difficult to model in automatic meshing method. So that's why we opted a manual meshing method. So in here, if you see, this is a typical geometry what we get, and which is converted into finite element model. What you can see here, it is split into countable number of parts. So here the total element count was 7,07,718, and the nodes are this much. You can see this. We have used first order tetrahedral elements for this analysis. So these are all the material properties we have used in this analysis. Yeah, so when come to the loading and boundary condition, so the objective of the study is to apply a 300 grams force at an inclination of plus 30 degree, minus 30 degree, or 0 degree with respect to the line which is connecting condyle and Pagonian point. So just for the demonstration purpose, I will be executing only one load case due to the limitation of time. So that is 300 grams of force applied at an inclination of plus 30 degree. So this is a typical boundary setup, or else after apply the constraints and boundary conditions. So I will switch over to the ANSYS ANSYS platform to demonstrate you how to execute this simulation. So starting from meshing to boundary condition setup, requesting the results and solving it. Well, so this is my ANSYS workbench. So here, as I told you, I have created the finite element model using manually I have meshed it using some other software. So I'm going to import it into the ANSYS workbench. And I'm connecting it to static structural objective. So as I told you in the previous slide, like now we have to have material properties, mesh, boundary conditions, and loadings. So we will check one by one. That is first is engineering data, that is material properties. So I have already made material properties before, because it takes quite a lot of effort to create. Here we have to input all the related material properties like Young's modulus, Poisson's ratio, etc. So we have modeled all the materials like articular cartilage, articular disc, cancellous bone, compact bone, etc. The geometry is loading. It will take a bit of a time. Sorry to keep you waited. Yes. Yeah. So now the geometry has been loaded into ANSYS workbench. So here you can see the measure model. So yeah, so this is an imported geometry, important model. So where we have to assign, the first step is to assign material properties for the respective components. Say for example, I will choose one component and I'll go to that corresponding body, and I have to, this is a compact bone, so I will assign it as a compact bone. So similarly, maybe you can select these bodies and assign them as a, tooth. So similarly, you have to select each and every bodies, and we have to assign the respective material properties to it. And so as I told you, the this is a chin point, and this is Pagonian point and condyle point. So where the reference line is this. So with respect to that reference line, plus 30 degree, minus 30 degree, and at 0 degree, we will be applying a chin up force. So well. So once we create the coordinate systems, so we have to create a connection between each and every components. So it is just a click of a button where the software will create a contact between each and every bodies. And this is a mesh we have imported it from external meshing file. So now we have to fix this. We have to have a boundary condition, that is the place where we have to fix it, and we have to apply a force. So first we're going to fix this component at this location. We have to select those spaces and apply a constraint that is completely fixed. And we have to apply a force now. So I am applying the force at chin location uh, with reference to the condyle and Pagonian point, which is I am going to select. I have created a customary coordinate system. So I have selected this angle, which is at plus 30 degree. So I am applying X as a 300 Newton. Sorry, 300 grams of force, which converts to 2.943 of Newton. So my mesh is ready, my contacts are ready, material assignments are ready. Then I have applied, I have fixed my components. I have applied a boundary condition, and loads are also applied. So now I want to request like what results I want from the solver. Like I am requesting for deformation, and I am requesting for overall stress, and also I also have a freedom of selecting an individual component and requesting for a stresses or displacement at that particular location. Say for example, now I will be requesting for stresses at this point. So now the entire process of setting up an FE analysis is completed. So now it is software turn to solve the problem. So after setting up the problem, so I just need to click on solve button. So the solver will take time, depending on the number of element, uh, the boundary conditions, it will take a little while of a time. So meanwhile, I have already previously I have solved the same problem, and I kept it for a demonstration purpose. So I'll switch over to that. Well, so after solving, the solver has given a output. So here you can see the total deformation of a structure. So I'm just going to play an animation out of it. So physically, you can imagine like, at this location, it has been fixed, and, chin up forces are applied on upward direction. So due to which the whole assembly is, moving outwards. This is a total deformation plot, what you're seeing. And we can also see the stresses, as a whole assembly, and it will also show the where exactly the maximum stress is. And we can also, component wise also we can check. So we can rotate it, and we have a lot of freedom in ANSYS tool, where you can but go to particular point and look at the stress values and report it. Now this is a bone part where in only in this particular component how much is the stress, we can rotate it and look at that particular point. So similarly, we can the software gives a lot of freedom, where you can customarily you can do limitless options, like these are teeth. Similarly, you can request for deformation, stresses, strains, principal stresses, and many other parameters. One second. Yes. So this is it. So as you can see the animation over here. So not only we can see the deformation and the stresses, we can see the animation, how exactly the assembly is behaving, how exactly the components are behaving, physical phenomenon, like we can witness the physical phenomena after applying particular loads and boundary conditions. So, and we can extract the images from the solver and put it into a record, like we can point out a different location, what are the stresses, we can put a tag on it, and